Jai Hind dear students. I am Dr. Supratim Saha, Associate Professor, Swami Vivekanand Subharati University, Meerut, and in today's lecture we are going to discuss about microwave filters. Before starting, let us see the topics and subtopics that we are going to study today. So these are the subtopics and topics that we are going to study today: microwave filter design, applications of microwave filter design, methods of microwave filter design, image parameter method basics, advantages, disadvantages, and conclusion. Now, what is a filter? A microwave filter. A microwave filter is a two-port network used to control the frequency response at a certain point in an RF or microwave system by providing transmission at frequencies within the pass band of the filter and attenuation in the stop band of the filter. Typical frequency responses include low pass, high pass, band pass, and band reject characteristics. So here in general, most RF and microwave filters are most often made up of one or more coupled resonators, and thus any technology that can be used to make resonators can also be used for making the filters. Moving on, for applications, the applications can be found in virtually and any type of RF or microwave communication, radar, or test and measurement system. As you can see, filters designed using the image parameter method consists of a cascade of simpler two-port filter sections to provide the desired cutoff frequencies and attenuation characteristics, but do not allow the specification of a particular frequency response over the complete operating range. Thus, although the procedure is relatively simple, the design of filters by the image parameter method often must be iterated many a times to achieve the desired results. A more modern procedure called the insertion loss method uses network synthesis techniques to design the filters with a completely specified frequency response. The design is simplified by beginning with a low pass filter, and the low pass filter prototypes that are normalized in terms of impedance and frequency. Now transformations are then applied to convert what? Convert the prototype design to the desired frequency range and impedance level. So this is all about the particulars about microwave filter design, and we are going to see some of the methods, some of the basic methods of this procedure. The basic two methods are the image parameter method and insertion loss method, as already discussed in the earlier slides. As we already know, the insertion loss method is the more modern one, but as of now we will start with the image parameter. So let us see in the diagram of image parameter method. As we can see, it offers filter design and specification involving pass band and stop band that we have already discussed in the previous slides. So let us move forward and start explaining the image parameter method. So the image parameter method, as you can see, involves the ABCD portions, and this entire two-port network is terminated in its image impedances. We will now use the currents I1 and I2, the voltages V1 and V2 in correspondence with the overall image of this particular process, and try to solve the equations that come along. Along with this entire process of image parameter method will be discussed, and we will later on discuss a summary of this particular method. Moving forward, the basics of image parameter method. If you see, The image parameter method will be involving the explanation where the port voltages and currents are related. How they are related? We all know that voltage is equal to current into resistance. Now the port voltages and currents are related here in the form of this following portion. As we can see from here, this portion will be associating with the voltage V1, and we can accordingly write V1 is equal to AV1 plus B into I2. That means parameter A multiplied by the voltage along with the combination of the other part of the diagram will be providing us V1 value. Similarly, I1 is equal to CV2 plus DI2. That means here I1 is nothing but corresponding with C into V2 and D into, and therefore this clear scenario gives us the equation I1 is equal to CV2 plus D into I2. In the next process, the input impedance at port 1 with port 2 terminated in ZI2 is, this is nothing but Z in 1. What we are discussing is the input impedance at port 1 with port 2. The input impedance in port 1 in port 2, this is nothing but Z in 1. So that is what we have discussed over here, that is Z in 1. And what is Z in 1? If you go back, Z in 1 is nothing but the ratio of V1 to I1, that is voltage V1 to current I1, and we can write it simply as V1 by I1. Again, V1 by I1, V1 we have already found out as AV2 plus VI2, and I1 is found out to be CV2 plus DI2. So these two combined here can be written as AV2 plus VI2 whole divided by CV2 plus DI2. This can be equated using the other portion of the diagram, that is, it will become the other portion of the diagram, that is combining the secondary portions of the diagram in the same process. So it will become A into ZI2 plus B whole divided by C into ZI2 plus D. So in this regard, the overall input impedance at port 1 with port 2 terminated is found out. Moving on, we are now going to find out the input impedance at port 1 with port 2 terminated in ZI2 in the other form. Here what we can do is we can replace the V1s with V2s, and it comes as V2 is equal to dV1 minus dy1. Similarly, I2 comes as minus CV1 plus A into I1. How we have got it over here? We have got it using interchanging these equations as well. That is also what we can do. As you can see that the changing of the various parameters from the above equations leads us to give us V2 is equal to dV1 minus dI1 and I2 is equal to minus CV1 plus AI1. Moving forward, the input impedance at port 2 with port 1 terminated in ZI1. That means the reverse of the first case scenario. The input impedance at port 2 with port 1 terminated. The input impedance at port 2 with port 1 terminated. This can be given by, as you can see, Z into. Where can we find Z into? We can find Z into here. This Z into can be implemented in the same way how we found out Z in 1, and because it is in the opposite, so minus V2 by I2 will be the equation. As you can see, when we started, it was for port 1 it was V1 by I1. For port 2 it is in the opposite, V2 by I2 represented by a negative sign. So this V2 can be given by the other parameters, and how we define them? It becomes D into V1 minus B into I1 and along with this C into V1 plus A into I1. This D into V1 minus B into I1 minus C into V1 plus A into I1. This sounds familiar, right? Similar thing we did at the time of this portion. So here also we replace the values of V1 and accordingly we calculate using the same method of formula from here and there, and found that it can be replaced as D into Z into I plus B whole divided by C into Z into I1 plus A. So this gives us the entire formula up to this point. Since V1 is equal to ZI1 and we desire that Z in 1 is equal to ZI1 and Z into is equal to ZI2. That is we are desiring this. That means we want this. So we can write ZI1 into CZI2 plus D is equal to AZI2 plus B. So while writing this, by interchanging this, what we can do is we can allocate the numbers in such a way that they fall in place all together one by one. So in the next step it becomes ZI1 into D minus B is equal to ZI2 A minus CZI. So this is the portion for the other half of the parameters that we were concerned with. Now solving for ZI1 and ZI2, it gives ZI1 is equal to under root of AB by CD and ZI2 is equal to under root of BD by AC. How we have got this? We have got this by this and from these equations combined with the overall portion of Zi and Z2. So in this way we find the solutions of Zy is equal to under root of AB by CD and Zi2 is equal to under root of BD by AC. Moving forward, with Zi2 is equal to DZIA divided by A, if the network is symmetric, then A is equal to B. That means if the network is completely symmetric, like a mirror image of each other, there is no difference of the two halves of the network. In that case, A is equal to B. How we can say that? We can say that like here. If both of them are similar, then we can write that it will be A is equal to D. And Zi1 is equal to Zi2 as expected. Obviously, if we are considering one part to be symmetrical, the outcomes will also be symmetrical and similar in nature. Now consider the voltage transfer function for a two-port network terminated in its image impedances. What will happen then? The output voltage at port 2 can be expressed as, but what is the output voltage at port 2? The output voltage at port 2 is V2. So the output voltage at port 2 can be expressed as V2 is equal to dV1 minus VI1. Here I1 can again be expressed with the help of V1. We can take V1 as common. So what we are left with? We are left with D minus B by Zi1 into V1. So this is the entire thing that we are left with. So in the next stage, we take the example and the figure of a two-port network terminated in its image impedances and drive with a voltage generator. What is the difference here? Here the difference is that it has been driven by a voltage generator. We are assuming that the same circuit is being implemented with the help of a voltage generator. So how the things change, we can see now. Since now we have V1 is equal to I1 Zi1, so the voltage ratio will be, obviously the input portion and the other portion is represented by V1 and V2. So it will be V2 by V1 is equal to D minus B by Zi1, that we already know. D minus B under root of CD by AB. Why? Because we already have seen that the values of Zi1 is equal to under root of AB by CD, and the value of Zi2 is equal to under root of BD by AC. So putting that here and putting them into good use, so we can find out the values to be D minus B into under root of CD by AB. We take it outside, take it common, and the final value becomes under root of D by A, bracket close, under root of AD minus under root of BC. Similarly, now we have got the voltage ratio. What if we want to go for the current ratio? The current ratio is I2 by I1 is equal to minus C into Vi by I1 plus A. So similarly, the other changes will be reflected as well, and this will result in minus CZIA plus A. Same process we apply. We put the values of Zi1 from here and put it back, that is under root of AB by CD, and put it back in this process, and we end up with under root of A by D, bracket close, under root of AD minus under root of BC, bracket closed. The factor under root of D by A occurs in reciprocal positions, can be interpreted as a transfer turns ratio. That means the factor D by A can be used in a reciprocal position and interpreted as a transformer turns ratio. Apart from this factor, we can define a propagation factor for the network as e to the power minus gamma is equal to this entire portion will be considered for this, that is under root of AD minus BC. So this sums up the calculation that we are concerned with. Finally, with gamma is equal to alpha plus j beta as usual, we can modify this equation. And why is it necessary? Because we need it in the symmetrical form. Okay, so e to the power beta is equal to 1 upon e to the power gamma is equal to 1 upon under root of AD minus under root of BC can be equated as AD minus BC whole divided by under root of AD minus under root of BC. These can be simplified to provide us with the final equation of under root of AD plus under root of BC. We need to remember that here all the four ports have been combined and not segregated. They appear as a summation form. Okay. We also have cos h of gamma is equal to e to the power gamma plus e to the power minus gamma whole divided by 2. Two important types of two-port networks are there. Okay. T and pi circuits which can be made in symmetric form. So we come here as the summary portion of the microwave filter design and image parameter method. So in summary, we see that in case of the image filters, depending on how many stages are there in the unit of cell that we see, it depends whether it is a broadband or a narrowband filter. So a clear classification, like we have said, between narrowband and the broadband filters cannot exactly be made for these kind of image filters. But the concept is very interesting because it is just like a transmission where we have a larger signal to work with. If we have a large number of signal of sections, then we can design certain attenuation in the soft band as well, and a certain cutoff frequency can also be considered. However, with the present day where we have the advanced technology for synthesizing our desired filter response, these filters are not that common because the technology has moved very fast. We have different methods which are more profoundly applicable, more efficient. So these kind of methods are in use today, but we have other options as well to implement. So in a nutshell, if we proceed towards the conclusion, the example of the filter called image filters, depending on how many stages of these are there of the image cells, it depends whether it is a broadband or a narrowband filter that we discussed already. So a clear classification, like we have said, between narrowband and the broadband filters cannot exactly be made for the image filters. Finally, the concept is very interesting. It is just like a transmission, but it is like we have a larger one to build, considering a large number of sections. So this brings us to the end of this topic. The topics that we have discussed, we can look at it once again. That is, we have discussed the microwave filter design, the applications of microwave filter design, the method of microwave filter design, image parameter method, the image parameter method basics, the various advantages and disadvantages, followed by the conclusion of this overall method. So I hope this lecture has been informative to you. In the coming lectures of this series, we will again be discussing some further points, some future topics of this subject of microwave theory and techniques. I hope you have learned something from this session, and we will continue similar lectures in the upcoming series of this subject. Thank you and Jai Hind.